As the next title, we will consider planar problems in elasticity. These planar problems are plane stress and strain. And why do we need these equations of elasticity, linear elasticity normally? They are fully three-dimensional equations, and they are applicable for a coordinate system shown here, x, y, z. But especially analytical solutions, most of the time cannot be derived for fully 3D case. And crack problems of practical interest, fracture mechanics problems are most of the time two-dimensional. You consider a specimen like this that contains a certain kind of crack, and under mode 1 loading, this can be treated as a 2D problem. It is possible if certain criteria are met, then you can define this as a two-dimensional problem. And that will simplify the equations. Some of the terms from the general differential equations, constitutive equations are going to be eliminated, and they will have a somewhat simpler set of governing equations for which analytical solutions can be found. And what are those conditions? What are the requirements needed to specify a problem as plane stress and or strain? A deformable body, a general shape, is shown here. And it says, first of all, it's either cylindrical or prismatic in z direction. And z is the axis, the cylinder axis. It says thickness is shown by b. And in planar problems, there are two limiting cases. B is either small or it's infinite. If it's small, sufficiently small, plane stress approximation can be applied. If B is sufficiently large, plane strain approximation is considered. And there's certain loading here. And the loading has no component in z direction. It should not have any, there shouldn't be any stresses in z direction like this. No loads on these surfaces. It's not a load. And the loading is independent of z. There should be no dependence on the z direction. So these are the cases for this could all be applicable for this crack problem, for example. So that's associated with the geometry and loading. If these conditions or requirements are all met, I can define either a plane stress problem or a plane strain problem. In the limiting case for which B approaches zero, we are dealing with plane stress elasticity problem. And in the other limit, as B goes to infinity, we define a problem of plane strain. And there are certain mathematical assumptions associated with plane stress and strain. If you consider plane stress, another remark, you don't need to consider the whole thickness. You can represent it as a cross-section if the problem is planar. So this could be plane stress and strain, and this is referred to as a planar elastic body. Everything is considered in this cross-section, XY plane. Now, we are not dealing, nothing is a function of Z in planar problems. For this reason, this is referred to as a two-dimensional case. And what are the simplifications for plane strain? The first, plane stress, the first question. In plane stress, thickness is small. Let's say that this is the thickness, and this is the Z direction. No loads are permitted on these faces. Therefore, on this surface, and this is Z. On this surface, sigma ZZ, normal stress, and shear stresses, sigma ZX and sigma ZY, they are 0. And they are 0 on the other surface, 0 here. All stresses with Z normal, they are 0 on both surfaces. And the main assumption is that there is not an appreciable significant variation within the domain. These stresses are also 0. They are assumed to be 0 within the domain as well. And as a consequence, this is the main assumption of plane stress within the volume of the body. Sigma ZZ, sigma ZX, and sigma ZY, they are all 0. That's the main assumption of plane stress. And the other components are assumed to be functions of only X and Y. Non-zero stress components in plane stress are sigma XX, sigma YY, sigma XY. These are also named as in-plane components. This is the in-plane cross-section. They are functions of X and Y. These three stresses are 0. And it will help simplify constitutive relations and general governing differential equations. For plane strain, we are looking into the opposite variation. Now, B is getting larger. It's not getting smaller. It's actually infinite. From a practical point of view, infinite B is not possible, but B can be sufficiently large. Therefore, plane strain is going to be applicable. If B is infinite, each cross-section is a plane of symmetry, and the displacement component in Z direction is 0 in the case of plane strain. Therefore, non-zero displacement components are U and V, and they are functions of only X and Y. Again, there is no Z dependence. Now, the assumption is on displacement and strain. If W is 0 and U and V are functions of X and Y, you can show that these strains should all be equal to 0. Epsilon Z, epsilon YZ, and epsilon XZ, strains associated with Z direction, they are all 0. And the other strains are functions of X and Y. Now, how is this possible? Keep these assumptions in mind. W is 0 and U and V are functions of X and Y. If you go back to the original results there, given epsilon Z or epsilon ZZ is, for example, dW dZ. And since W is 0, this is 0. Gamma X Z du dz plus dw dx. U is not a function of z, and w is 0. Thus, this is also 0, and in a similar way, this shear strain is also 0. Non-zero components are the in-plane components, epsilon xx, epsilon yy, gamma xy. Now we have ended up with some simplifications, and we will apply them now on the constitutive relations. These are the simplifications for plane strain. And this set of results. And these are the simplifications for plane stress. First of all, we can simplify constitutive relations. Constitutive relations are another way of referring to Hooke's law. The title, Constitutive Relations. And Hooke's law is the mathematical representation of linear elastic behavior. And we can simplify Hooke's law for plane stress and strain problems. What's Hooke's law for plane stress and strain? Generalized Hooke's law. First of all, we assume that the materials we are dealing with are isotropic. And they are homogeneous materials. And how many elastic constants are needed for isotropic materials? That's a question for you. Yes, Alionov gave the answer. We need 2 constants, and I can write them here, E, nu, another one is G. Now, but I think it's not completely visible, but we'll write it one more time. E and nu, or E, nu, and E is modulus of elasticity, and nu is Poisson's ratio. Therefore, you know that this is the general Hooke's law for a 3-dimensional state of stress. Epsilon x is 1 over E sigma x minus nu times sigma y plus sigma z. This is generalized Hooke's law of epsilon x, epsilon y, epsilon z, and shear strains, 1 over epsilon xy, for example, is 1 over 2 mu sigma xy, epsilon yz, epsilon xz. They can be written. This is 3-dimensional. E is modulus of elasticity, nu is Poisson's ratio, and nu is shear modulus. But these are related. As we have said, only 2 constants, independent constants. Because mu is E over 2 times 1 plus nu. It's given here. E over mu is E over 2 times 1 plus nu, or 1 over 2 mu is 1 plus mu over E. So they are related. And mu is shear modulus. But these are general constitutive relations or generalized Hooke's law for isotropic materials, and they are simplified for plane stress. For example, for plane stress, sigma z, sigma yz, and sigma xz. They are all 0, which means that epsilon x becomes 1 over E sigma x minus nu times sigma y, here, that's shown here. Epsilon y is 1 over E sigma y minus nu times sigma x. Epsilon xy is 1 over 2 mu sigma xy. These are the simplified relations, constitutive relations for plane stress. And another simplification for plane strain, this is also possible. For plane strain, we have shown that epsilon z is 0. Epsilon z is 1 over e sigma z minus nu times sigma x plus sigma y, 0. You can find sigma z as nu times sigma x plus sigma y. It's given by this expression for plane strain. Substitute this into epsilon x and epsilon y and simplify it. You'll end up with this form. Epsilon x is 1 over e, 1 minus nu squared sigma x minus nu times 1 plus nu sigma y. From y is written in terms of sigma x and sigma y. And epsilon xy is 1 over 2 mu sigma xy. We have essentially the same structures here. This is for plane strain. And for plane stress. Same structures with different constants. And we can express these results by a single set of equations. This is another way of considering plane stress and strain in elasticity. The equations are written in this form. For example, epsilon x is 1 over 8 mu kappa here. It will be defined. Kappa plus 1 sigma x minus 3 minus kappa sigma y. This kappa is 3 minus nu over 1 plus nu for plane stress. And 3 minus 4 nu for plane strain. Now, for the uniform notation, this is referred to as Kolossov's constant. Constitutive relations or generalized Hooke's law valid for plane stress and strain. And you need to change only kappa here. If you take 3 minus 4 mu, you'll get the equations for plane strain. If you assume that it's 3 minus nu or 1 plus nu, you'll find the equations for plane stress. Therefore, this is a convenient way of expressing generalized Hooke's law for planar problems of elasticity. In a planar problem, we eliminate the dependence on the axis coordinates, z coordinates. Everything is assumed to be function of x and y. So you have two-dimensionality. Your specimen with no variation in loading in z direction and no loading in z direction can be constructed as a planar specimen, a plane stress specimen or a plane strain specimen. And there's a crack here or a groove. How can I further simplify the governing equations by applying these constitutive relations? Any questions about these results or about plane stress and strain in general? This is the end of the lecture, and we will consider equilibrium equations and differential relations in the next hour.